Let's invite our next speaker, my colleague MVN Murthy, Professor MVN Murthy, and nature of the neutrino is going to raise the question, is it a Dirac neutrino or a Majorana neutrino?
Thank you very much for inviting me to speak at this symposium. This work is done with my collaborator, Professor C.S. Kim from Seoul, and Divya Kripa Sahu, who was a former student of IMSC. So here is a photograph which you may have seen already. This is Professor Alladi Ramakrishnan with all his students, and I am his grand student. And my advisor was G. Ramachandran, who is here in this photograph. And of course, you can recognize Balachandran here. And this is Professor Devanathan, who was Parthasarathi's advisor. So this session has all the grand students of Professor Alladi Ramakrishnan. And the academic family of Professor Alladi Ramakrishnan still continues because there is Professor Ravindran and then Professor Indumati, and I hope it continues even afterwards. So we all belong to the same academic family of Professor Alladi Ramakrishnan, and I'm very proud of it. And also want to dedicate this talk to the memory of two GRs who guided me over time, late Professor G. Ramachandran and late Professor G. Rajashekaran, who passed away just a few months back. So here is my talk. Since it's a mixed audience, I will spend some time on the introduction on neutrino, a decade of discovery, which is basically introduction, and also neutrino, the status of neutrino in the standard model. And then I go to this question, whether it is a Dirac type particle or a Majorana type particle. What it means is that whether neutrino is its own antiparticle or there exists an antiparticle distinct from the neutrino. That is what we mean by Majorana and Dirac. And this is an open question. None of the experiments until today have been able to decipher whether it is Dirac or Majorana, in spite of the fact that large number of experiments are still ongoing. And it appears that there is a constraint, which it's a theorem. It's called as the Dirac-Majorana confusion theorem. And this has been assumed for the last 40 years. And what I'll do is I'll show an exception wherein you can overcome the constraint of this theorem and decipher the nature of the neutrino, whether it's Dirac or Majorana. It's a way out rather than telling you that it has already been done. So here are the references in the last 1 year that we have done. So let me begin with the decade of the discovery. For people who don't know about neutrino, neutrino discovery happened through the beta decay process where a nucleus changes into another nucleus, emitting an electron. This electron is detected and it has a continuous spectrum. And that was a puzzle because if you had only this daughter nucleus and the electron, then this electron will be a line spectrum. It will have well-defined energy. But the fact that it has continuous energy means that there must be one more particle through which it shares energy, and therefore the continuous spectrum comes. And Pauli was the one who first proposed that there should be a particle here, and since charge is already conserved, it should be a neutral particle. And in fact, it turns out that here in this case, it has to be an antineutrino to conserve the lepton number. And also you can make the argument through angular momentum, and large amount of data was explained through this proposal of Pauli. And in fact, for more than 2 decades, Meitner, Hahn, Chadwick, all these people had worked on the beta decay. And at the time of, after Pauli proposed, immediately Fermi came up with the theory of the beta decay, which is the first version of the theory of weak interactions. It is a stepping stone towards the standard model, the first stepping stone towards the standard model of particle physics. And Pauli's solution was that there is an extremely light neutral particle and is also part of the nucleus. This is not necessarily true, but that's what he said. And Pauli initially called it neutron, but by that time the name neutron was taken by the constituent of the nucleus. So Amaldi and Fermi called it neutrino or the little neutron. Basically, it's a neutral particle. And weak interactions were formulated. And in 1934, Irene and Frederick Curie observed the other decay wherein a positron is emitted instead of an electron. Basically, the nucleus then loses one charge instead of acquiring one charge, and this is called as the inverse beta decay. And in 1934, Wick of the Wick expansion, this was one of his first works. Wick proposed that the electron capture or inverse beta decay, and it was actually observed, the inverse beta decay was observed by Alvarez in 1937. So, I'm still in the new decade, and in 1935, Maria Geppert-Mayer, the one who got the Nobel Prize for the shell model, and the second woman in physics to get it, and second woman in all of last century. And she proposed that not only beta decay, double beta decay can occur. Double means that there are 2 electrons and 2 antineutrinos. Now, in 1937, Ettore Majorana, who was considered a genius by Fermi, proposed that because neutrino is a neutral particle, it may be its own antiparticle. Now, this is a surprising thing because we know that particles can be their own antiparticles, but they are always bosons, like photon, like pi naught. These are all bosons. But a fundamental particle, which is a fermion, can be its own antiparticle only if it doesn't have any charge. Because the moment you have charge, the antiparticle will have opposite charge. When it is neutral, then the antiparticle is also neutral, then there is a possibility that nu equals nu bar. I'll explain how this comes about. This is the only fundamental fermion in standard model that can be its own antiparticle. In 1939, following this idea, Furry proposed that neutrino-less double beta decay can occur, which means this neutrino, because it is its own antiparticle, it can virtually annihilate itself, leaving you with only 2 electrons in the final state in this double beta decay. Okay, this is called as the neutrino-less double beta decay. It's an SNO experiment. The moment you observe this neutrino-less double beta decay, you know that the neutrinos are Majorana particles and not Dirac. Of course, you can either have Dirac or Majorana, and I'm talking about only that scenario. So this has not yet been observed. So the question is still open, is neutrino its own antiparticle? Now, the new decade ends with the stellar energy production scenario where the neutrinos and the weak interaction play the central role in the energy production in stars. And this was completed by Bethe, first by Critchfield and Bethe, and later Bethe wrote this monumental paper which completely gave all the reactions in the sun which are responsible for the energy productions. Today we talk about solar energy, and here is the scenario by which the solar energy is produced. So within the standard model, I'm jumping about 3 or 4 decades here. There are 3 families which are called leptons. There is electron, there is muon and tau, and of course they are antiparticles. And associated with this electron, there is a neutrino which we call as nu e, nu mu, and nu tau. And so there are 3 active flavors and their antiparticles. Now, within the standard model, the mass of neutrino is identically 0 for all flavors. Flavors by which we mean this electron, muon, and tau. And they are also, because the mass is 0, they are all left-handed. Of course, that they are left-handed is an experimental fact. It could have been the other way also, but it turns out that nature prefers left-handedness for neutrinos. Therefore, the antineutrinos are right-handed, and you can go from neutrino to antineutrino, which is a particle-antiparticle transformation, through this CPT transformation. But these neutrinos, experimentally we know, unlike in the standard model, they have non-zero mass. We know that. And not only that, they have a funny behavior that the flavors, that nu e, nu mu, and nu tau, they tend to mix while propagating. Now, this is a funny phenomenon, neither of which is within the standard model, within the ambit of the standard model. So therefore, neutrinos provide a window to physics beyond the standard model. Because of this mixing, the neutrinos oscillate, which means what is produced as an electron neutrino at the source, we may detect if the large number of them are coming, say n number, so n1 of them may be in the electron flavor, n2 may be detected in muon flavor. Of course, n1 plus n2 being equal to n because they are fermions. So that is a possibility, and that's called as the neutrino oscillation. They change flavor as they evolve and continuously. So therefore, depending on where you put your detector, you may find different mixtures. And this has been observed, and it's very peculiar. It's a quantum mechanical phenomenon, but it cannot be understood through the present day formulation of the standard model. So are there more flavors? I said there are 3 active flavors. There may be more flavors, but they may be sterile. Sterile in the sense that they do not have the interactions which we have specified within the standard model. Now, if that is the case, is that a window to dark matter? Is this mixing a window to the dark matter? Here we are not looking at interaction, we are looking at it through the mixing, where the sterile neutrinos may form, if not all of dark matter, may form some of dark matter. They need to have some mass so that they are warm, but it is possible. So therefore, there is a window to the dark matter through the neutrino sector. And then of course the origin of neutrino mass. We know experimentally that they have mass, which is non-zero, but question is, what is the mechanism of these mass? Is it the usual Higgs mechanism that we know in standard model, or is it a seesaw or something else? These are all mechanisms to generate the neutrino mass, some of which require neutrino to be Majorana, and some of which require neutrino to be of Dirac type. So then one of the important questions that I have listed here, what is the nature of the neutrino? Is it Dirac, which means particle and antiparticle are distinct, or is it Majorana when particle is identical to antiparticle? That means it is its own antiparticle. This is the focus of my talk, and neutrinos, if this is the case, may provide the key to understand the matter domination in the universe. So this is a question which is yet an unanswered question, which is that in the universe, if you see, more or less everywhere you see is matter dominated. You don't see antimatter galaxies, antimatter stars, etc. So naturally, there is an asymmetry which was not there at the time of its origin. So therefore, how did this come about? And the key may lie with the nature of the neutrino. So here is just a summary of the neutrino properties. We don't know what the mass of the neutrinos, these 3 active neutrinos are in absolute terms. But what we know experimentally is that there is some difference. For example, m2 squared and m3 squared differ by about 10 to the power minus 3 electron volt squared. This is a squares, mass square difference. And similarly, m1 and m2 may differ by 10 to the power minus 5 electron volt square. We don't know the absolute scale of this, but we know only the differences. And we also don't know which is heavier, which is lighter, etc. There are questions. But there is a scale here. There is a mass scale here. We don't know the absolute value of individual masses. And neutrinos mix. This is one slide summary of what we know from gamut of experiments. In fact, huge number of experiments, solar, atmospheric, reactor, accelerator experiments within the framework of 3 active neutrino flavors. So let's go to the nature of the neutrino. Why is it that we can consider 2 possibilities, Dirac and Majorana? That comes from the fact that the Dirac equation, it describes the spin half fermions. Neutrino is a spin half fermion. And it's a 4-component Dirac equation. And here is the equation. And this is the Clifford algebra, which people were talking about earlier, of gamma matrices. And the psi is usually a 4-component spinor, unless the mass is 0. If the mass is 0, the 4-component solution reduces to a 2-component one, because the equation decouples into 2-component equations, and that is called as the Weyl basis. I mean, you can work in the Weyl basis when mass is 0. However, when neutrino's mass is non-zero, which is what the experiments are telling us, the equation allows complex 4-component solutions. This is called as the Dirac basis. And it was also pointed out, this is Majorana, who pointed out that when mass is not equal to 0, it is possible to choose the set of gamma matrices of this Clifford algebra in such a way that you have real solutions. Then these will have imaginary elements, but psi can be equal to psi star, meaning real solutions, which means nu equals nu bar. These are the two different types of solutions that the Dirac equation allows. And the neutrino is neutral, hence it can either reside in this or in this, and we don't know the answer yet. None of the experiments measuring oscillations presently can decipher the fundamental nature of the neutrino. And I don't know if there are many students here. If you want to know more about this, there is an absolutely superb pedagogic review by Palash Pal. It is in Archive, published about 2010. I think it's also published in American Journal of Physics. It's worth reading for those who are interested in it. So, what are the experimental tests which can distinguish between Dirac and Majorana? So, double beta decay, Maria Mayer proposed this. This is a standard allowed process in the standard model. There are no violations of any quantum numbers here. So, this is allowed and this has been observed. What is not observed is this, which is called as the zero or neutrino-less double beta decay, and this has not been observed, and this is forbidden within the standard model because it violates what is called as the lepton number. There are no leptons in the initial state, which is just a nucleus, whereas there are two electrons in the final state which carry the lepton number, and therefore this is a delta L equal to 2 transition, which is forbidden within the standard model. The rate for NDBD has been calculated theoretically. It's proportional to the neutrino mass, which we know is tiny because the mass difference, through the mass differences we can see that, but it's unknown. So therefore, the whole rate for this process depends on an unknown quantity. Not only that, there are theoretical uncertainties that plague the model-dependent nuclear matrix elements. So if observed, nevertheless, if this is observed, it's an yes-no experiment because this can only go through when neutrino is Majorana. So what is the present status of this experiment? This has been observed with a lifetime of 10 to the power 18 to 10 to the power 24 years. Well, so basically, you don't wait for that long. You just put large amount of the material, and even if you see one, that tells you how to put these limits. That's the half-life. And zero nu has not been observed yet. Experiments are going on since 1980s. The present limit is that the half-life, if neutrino double beta decay occurs, it's more than 10 to the power 26 years. And this is the latest limit set by the Kamland experiment in Japan. So there are also many other proposals which are running and some in progress. Like there's a collaboration Tintin led by TIFR people. This is in the R&D stage. And there are people who have suggested meson decays, M plus going to M minus, mu plus, which can go through similar to neutrino-less double beta decay. There are no nuclear uncertainties, but doing this experiment is extremely effective. My collaborator Kim has done a lot of work in this area. So, what is our approach? And here it is. We use quantum statistics. If the neutrino is Dirac, then neutrino and antineutrino are distinct particles. There's no Pauli exclusion which operates there. On the other hand, if the neutrino is Majorana, then it's its own antiparticle. So you have to impose Pauli exclusion principle. So you have to choose processes where you can impose Pauli exclusion principle such that you can use this to distinguish between Dirac and neutrino. So you must have a nu bar pair in the final state. If the neutrino is Dirac, then there is they are distinct. In this case, they are identical. And the role of quantum mechanics, quantum statistics is different for Dirac and Majorana type. It should be possible to experimentally, therefore, distinguish between Dirac and Majorana case. Note, only one of them can be realized in principle. That's the only case I am considering, not the case where there can be mixtures. Now, caution. I continue to use the notation nu bar even when I am talking about Majorana neutrino, but with the proviso that it is the same as nu in the Majorana case. So, just so that there is no confusion. So, here is implementation of the Pauli principle. Consider an arbitrary standard model process of this type. X is a particle which is decaying. Y may be one particle or two particles. It can be left unknown. And there is a nu and a nu bar pair with momentum P1 and P2 in the final state. This nu bar is the same as nu if it's Majorana otherwise it's distinct if this thing. So the amplitude for this process, probability amplitude, I'll just denote it by this notation. Md is m of P1, P2. In the Majorana case, since nu is equal to nu bar, you have to antisymmetrize this, and that is m of P1 comma P2, m P2 comma P1. P1 and P2 are the 4 momenta of nu bar pair, suppressing all other indices. Note, only 4 momenta are exchanged in the amplitude when you use quantum field theory rules. So, following the rules of quantum field theory, you can calculate the probabilities of the rates. Md squared mod squared is this. In the Majorana case, you will have a direct term which is m squared P1 P2, then another term which is exchange of P1 P2, but because we started with 2 terms, there will be an interference term, and that interference term is given by this. Okay. Now, the interference term always mixes vector and axial parts of the current. Therefore, it is always independent. You can make a statement independent of any process that it's proportional to the neutrino mass square. Therefore, this, even though it distinguishes between Dirac and Majorana, it is always proportional to m nu square. So, it's like double beta decay. It's a m nu may be very small, very close to 0. Then what will you do? So, the 2 cases are distinguishable in principle, but is it observable? Now, at this stage, at the amplitude stage, you can see that m of P1 P2 mod squared is not the same as m of P2 P1, because we have interchanged this. These 2 reside in very different kinematic regimes. So, therefore, this is only m of P1 P2. Direct term is there, but this is half of direct, half of exchange. So, these 2 are not different. Can we observe this difference? Can we use this to find out the nature of the neutrino? So, that is what I am saying. Direct term is not the same as exchange term, because P1 is not equal to P2. I mean, unless P1 equals P2, that's a different case. But nu bar pair is not observable, so integrate over all the allowed values of P1 and P2. But here what happens is that the allowed values of P1 and P2 are arbitrary designation of kinematic momenta. So, they go through the same range. So, when you integrate over them, the direct term and the exchange term, since they cover the full phase space and the P1 P2 space, they will be equal, and the kinematic range of P1 P2 is the same. This leads to a theorem which is called as the practical Dirac and Majorana confusion theorem. And the theorem states this, that because md squared minus mm squared, after integrating over P1 and P2, because the difference between exchange and direct disappears, after integrating over, the difference between these 2 is equal to only what is given by the interference term, which is of course proportional to m nu square. So, therefore, we are back to square one, where you have this theorem by looking at the total decay rate or any kinematic test of the process allowed in the SM. It is practically impossible to distinguish between Dirac and Majorana neutrinos in the limit of neutrino mass going to 0. If the mass goes to 0, there is no way you can do it. So, but this theorem, which was proposed in 84 by colleagues of Balachandran, Boris Kaiser, Schrock and others, has been in vogue for the last 40 years. There is no general process independent proof, except as outlined in. This is about as clear a proof as it can be given, which is there in our paper. But I haven't seen a better proof than that. But is there a way we can avoid this constraint? Can we actually determine P1 and P2 in an experiment so that we don't need to integrate? So, when P1 and P2 are different, then obviously you can have a direct measure of the Dirac type or the Majorana type and see the difference experimentally. So, can we evade it? So, there have been previous attempts, none of which have been successful, except in the case of Chabra and Babu, who make the same statement as we make. They also point out that if nu bar momenta are known, then the theorem constraint can be avoided. And there are other tests which are also proposed by our colleagues H.S. Mani and N. Gupta. So, here is where we are. The theorem is bad news, since any distinction between Dirac and Majorana type depends on the tiny unknown neutrino mass. The only hope is then double beta decay and similar suggestions. However, there is a way out. We can measure the neutrino parameters indirectly in some kinematic regime. We show this using an example allowed in standard model. Unlike double beta decay, the example, it's allowed in standard model. That means if the neutrino is Dirac type, you use QFT and calculate everything. So note, unlike NDBD, there is no lepton number violation. So here is the process. One of the processes, there are many processes, but let me take this example. And these are all non-resonant diagrams, but when you are dealing with hadrons, you will also have resonant diagrams, which I haven't put it here. So consider the decay of B meson, which goes to mu plus, mu minus, nu bar. No lepton number violation. It's a standard model allowed process, which is being observed as we are sitting here today in LHC B and other B factories. Okay? So nothing unusual about it, no problems here, and standard model tells you how to calculate the whole thing, so no theoretical uncertainties. And there are many other processes you can do this. And remember, it's a 4-body final state, not a 2-body final state. If it's only nu bar in the final state, then you can't observe it. There's no kinematic way of observing it. You need other particles which tell you what the momenta of the neutrinos is. And that is the reason why you have to have this mu plus and mu minus. So once you have that, here, there's a Gedanken example I'll give you. Mu plus and mu minus are going in the backward direction, and let's assume that the neutrino and antineutrino, I'm using the Dirac notation, are going in the same direction with the same momenta. Now you look at the amplitude of MD, and MD squared you can calculate for this process is the Dirac type, then it's a non-zero thing which depends on the values of this momenta. But in the Majorana case, this is 0. So there is a difference which is in front. But this is a Gedanken example because I cannot find a kinematic regime in which these two are going collinear. That is the problem. So we go to another kinematic regime where it is possible. Look at this back-to-back configuration. No need to observe the neutrinos. We know everything except this angle theta. So what is the back-to-back regime? Mu plus is going in this direction, mu minus is going in this direction. So therefore, this is a decay at rest. The neutrinos to conserve momentum, they should also go in the equal and opposite direction. This is the nu bar, but it may go at any angle. Now the angle is the only indeterminate here. Everything, the neutrino energy is determined, neutrino momentum is determined. The momenta are opposite to each other, energy is the same. And they are completely determined, like P nu squared is this. It may depend on m nu, but this m nu is very small, but these can be very large. So therefore, momenta of the neutrinos are determined by the momenta of mu plus mu minus. Neutrino is observable indirectly. Now, you can also show this in helicity analysis. You get a very simple result, but time is not there. So we can carry out this calculation. Whatever I have said, I can start with this process BDK. I can go from starting with the Feynman rules, write the amplitude, do the full calculation, keeping P1 and P2 fixed for a given P1, P2, and then I can calculate it when P1 is minus P2, the three momenta are opposite, equal and opposite. I can do the calculation. So this calculation has been done. In fact, Divya Krupa is an expert in such calculations, and he was trained by another expert who was here, Professor Rahul Sinha. So, and we gone through this many times, and it turns out that the energy angular distribution, this requires detection of the direction of the neutrino, which may happen in future. With the improvement in technology, it is possible. So we give that also. So you can see that when it is Majorana, it has a different form than when it is Dirac. And now, since we don't observe this angle, let us integrate over that. It's a planar process. Angle integration is trivial, 0 to pi. So once you integrate over it, you can see that the energy distribution is given by a function which is simply a function of energy and momenta here, and it is different for Dirac type and the Majorana type. The integrated distribution, which is easily observed, is not proportional to m nu squared. So this evades the theorem constraint, the Dirac-Majorana theorem constraint completely. Okay? So, in principle, this is, now it is not Gedanken. Even in practice, in principle and in practice, this is an observable, and therefore you should be able to distinguish and establish the nature of neutrino, whether it is Dirac or Majorana. Okay, what is the problem? The problem, okay, here is our calculation. You can see that the angular distributions are very different, and the energy distribution which is obtained after angle integration is actually, there is a order of magnitude difference between Majorana and Dirac. And the shapes, even though they are the same, the slopes are very different at different energies. So even if you can establish the slope, that will tell you whether it's Majorana or Dirac. So there are other possibilities, but the branching ratio is very small because you are only looking at one point in the phase space. So what you should do is that, so that's not a handicap, that can be done. I mean, you need very high luminosity to increase this thing, and in our estimate about a factor of 10 increase in luminosity in LHCb, we will do this, but that is a arduous task. So the branching ratio is small, and there is a form factor dependence which should be close to 1. It is not orders of magnitude, and in principle you can increase the probability of observing these things by combining with B0 and B0 bar decay, both of them, as well as looking at E plus E minus going to nu E bar. Now, why did we look at mu plus mu minus? Because muons are the least ionizing particles. So they are the easiest to detect. So experimentally muons are the simplest. But you can also have E plus E minus. Anything where mu plus mu minus can come, you will have E plus E minus, and therefore, unless there is a threshold problem. So this will also be there, and therefore this increases the branching ratio by 4-fold. You can go to some other decays like J psi going to mu plus mu minus. J psi is spin 1, unlike B meson, which is a pseudoscalar particle. So here the branching ratio is much more favorable, and this is already there going on in Bell 2. And branching ratio of upsilon going to mu plus mu minus is also not bad. It's only a few percent, not as small as here. So therefore, you can look at any of these vector meson decays going to mu plus mu minus, pseudoscalar meson decays going to mu plus mu minus. This nu bar will be hidden there. So the experiments are already ongoing, which means the statistics is getting collected. It's a question of how many years you want to wait for the statistics. So that means there are experiments which are already looking at this question. There is nothing new is needed. You do not need that uncertainty of double beta decay in order to establish the nature of the neutrino, whether it is Dirac or Majorana. And there are no theoretical uncertainties because we can use quantum field theory or standard model to do the calculation. So this is the summary. Of course, here is all the papers which follow all the development here, starting from Boris Kaiser in 82, Rosen in 82, Chabra and Babu in 1992, and our paper in 2022. You can see the number of years here, it's about 40. And so what the flow chart is a summary. Choose a process involving neutrinos. You should have nu and nu bar in the final state. Apply statistics, and once you apply the statistics, you can see that you can distinguish between Dirac and Majorana. If you integrate and do not determine the momenta of the neutrino, if you have that difficulty, then of course the rate or the difference between them will be proportional to m nu square, which is very small. So moral of the story, quantum statistical property, I mean, this is one of the things that we keep emphasizing because so many questions are asked about the limit of m nu going to 0. I think that's a red herring because when m nu goes to 0, you are dealing with different animal. They are 2-component neutrinos and degrees of freedom are different. When m nu is not equal to 0, you have these two possibilities, and quantum statistics is something that's an intrinsic property of the particle, depends only on the spin of the particle. It cannot depend on any dimensional parameter. So therefore, this actually provides a way out to determine the nature of the neutrino, which is actually quite a fundamental problem. I discussed much of these things and also the slides, etc., with Professor Mani, Professor Rajshekaran. Back and forth we went, and Professor Vivek Datta. I would like to thank them for their inputs. Thank you very much.
Thank you for a very comprehensive talk. Any questions from the audience? Oh, sorry.
So once again, I got to say that my question will be very naive. I'm not any knowledge of physics. So it's a question of understanding this dichotomy. So you started off your title, Dirac or Majorana. So is this dichotomy due to the fact that we know that neutrinos exist in both forms, but given a neutrino, we're not able to decide in which category it is? Or is it that all neutrinos must be in one of two forms, but we are not able to decide which form it is?
Yes.
So what is the
second part.
The second
The
part.
neutrinos have to be either Dirac or Majorana.
All neutrinos.
All neutrinos. Okay. So it's the second part that we are trying to decide. But of course, you can take the first part of the question and also ask that, I don't know how to deal with it. But if you tell me that it's either Dirac or Majorana, then I have a way of determining whether it is Dirac or Majorana, and that is this.
Okay, I have slight problem with the presentation material. In the limit of m nu going to 0,
Yeah.
are they different results?
M nu going to 0, there is no Dirac and Majorana. M nu equal to 0. Exactly.
Yeah.
There's only while
No, in your calculation,
Yeah.
if you take m nu is equal to 0, what happens?
the difference survives.
Huh?
The difference survives.
Survives. Well, that is what my problem.
That is where the quantum statistics.
No, that's where my problem is.
Yes.
That's where I have my doubt, because next time I'm going to speak.
Yes.
It's effectively at that time a spin 1 particle decaying to 2 massless Majorana.
Yeah.
Okay, that is not possible within the Poincare group theory.
Yeah, but you
representation.
don't have a massless Majorana.
No, in the limit also it should go to 0. That's what I'm saying.
No.
There is no possibility.
This-
Okay, let me come to
This
that.
is a debate which is going on between us and people like Akhmedov and Smirnov. But now I think we have more or less settled kind of that debate.
No, it cannot be, because I'll come to that part. I have my doubts about it.
Yeah.
Okay, that's it.
Just a clarifying question. In your analysis, you considered the mu plus mu minus,
Yeah.
just the energies, but we can in principle know if they're spin, that means they're helicities as well.
Yes.
And
Yeah, we sum over all the spins.
right,
Yeah.
but if you don't
If you don't, yeah.
accentuate your result,
We haven't checked that.
okay,
Only thing is the expressions are so long
okay,
that we have not been able to continue it by you're saying that you look at the polarization of mu plus. With that part we have not gone into, but that question was also asked by one of the referees. Can you do it so that you can expand the difference? Yeah.
experimentally that's possible.
Yes, it is possible. Yeah.
Murthy, I was just wondering, 2 slides before you showed the branching ratio to mu plus mu minus, I think. Yeah, no, the next one.
Yeah.
Yeah, here. Like maybe the J psi or upsilon. So that is only mu plus mu minus, right? Without the neutrinos, or does it?
Yeah, but that will be part of this, right?
Yes, but
What
the branching.
they have observed is branching ratio for going to mu plus mu minus.
Yes, but with
But it
mu
will-
nu bar, it will be suppressed further, right?
Huh? Yeah, it will be
But how much is the suppression?
in this case, I don't know. I don't remember the number yet.
Okay.
But in this case, going to mu plus mu minus branching ratio itself is small. Whereas here it is not that small. So that way you can increase the branching ratio to mu plus mu minus mu nu bar also. Yeah.
Okay.
We have to do the calculation for this to check what fraction of that will be in the 4-body state. Yeah.
I was trying to think through this again. Okay? If I take the beginner representations, okay, for a massless particle spin half, okay, it is characterized by helicity. Spin. So, what is the characteristic in that context? Then there is only one representation given by the helicity. So, what are these? What is the distinction between Majorana and Dirac from the beginner theory?
From when you have massless neutrinos, there's no distinction.
There is no distinction, right?
There's no distinction.
That's what I was thinking.
There's no, I mean, Majorana neutrinos don't exist when you have massless neutrinos.
No, you can't say that.
Right?
Because from the representation theory point of view,
Huh.
there is something which you can describe either by 4 component or 2 component, as you like.
Yeah.
But they are the same because the 2 component can be separated separated into real and imaginary parts. That will give you the 4 component. Is there anything more than that?
No, here when you look at the solutions with m not equal to 0, it allows real solutions, right? And that is what you call as the Majorana.
What I am saying.
And what we are saying is that you just use that fact that mass is non-zero, so therefore real solutions exist. Therefore, it can Majorana neutrinos can exist, and
So
that's all we are using here. We are not doing anything more. Now, once you do that, then we go into the quantum statistics part of it. You give me that, we go to quantum statistics part of it. We use the standard Feynman rules that's given in standard model. Do the calculation. In the calculation, you can put mu equal to 0, but the difference is non-zero. I mean, my kinematic choice of back-to-back is different. That is my choice to see what the neutrino momenta is. So I don't even need to do that. I just calculate the amplitude square for the 2 processes with and without Pauli exclusion principle. And that difference does not go to 0 when m nu goes to 0. Actual proper calculation. So that is what I am looking at.
I am not asking about your calculation.
Yeah.
I am talking about beginner theory for massless representations of the Poincare group. Directly, I don't have a field. I just have a representation theory. Yeah. So for a massless spin half particle, there is only one representation, massless spin half, with helicity, given by helicity.
Yeah.
And
You
that
can,
you can call in what you like.
No. The one thing is that you have a symmetry there. You see, they are all chiral fermions. When mass is not 0, they are not chiral fermions. Chirality is not a symmetry.
And in the beginner theory,
Okay,
what is the
and
difference?
that's important when you are looking at Majorana neutrinos.
I am not sure. What is the difference in the beginner theory of massless particles?
What is it?
In the beginner theory of massless free particles,
Yeah.
what is the difference? There is no field.
I mean, that's a 2-component object that you are talking about.
That's
Whereas
it.
here it's a 4-component object.
Sorry?
That's the difference. Huh. Massless
That's what I'm
part.
saying.
That's correct.
That's what I'm saying.
Yeah, there's no distinction.
So it's a language. It's just
Yeah.
a language.
That's right. Dirac and Majorana collapse into one.
There is no language.
Mass is equal to
That is
0.
why I said before, if you write a Dirac, there is a complex structure which you can combine into 2 components, or you can leave it as it is. It doesn't
Yeah.
make any difference. Massless free. You agree? You agree, no?
Yeah.
Comment to this. Added to all this theory is renormalization. There is a question of renormalization of parameters. No, the masses do get it. They also run here once you put the masses. And then, if you then go to 0, there can be a distinction, and we should be open-minded about this matter.
Yeah, we went through this with Akhmedev and others many times. I think we have now understood at least, you separate our kinematic part, that at the level of probabilities, there is a difference when mass is non-zero between Dirac type. And I think to a great extent we.
Oh, okay, let's thank the speaker once more.
Thank you very much.
I request Professor Ravindran to present a small gift to Professor Murthy. It's a legacy of Alladi Ramakrishnan.
Thank you very much.